Thank you so much for that kind introduction. I hope my aspirin will kick in soon. I will be less zombie-esque as in the first 20 minutes of this talk. So I've been at the really at the intersection between reinforcement learning and robotics for quite a while by now. In fact, it's so bad that the robotics people say, oh, he's a machine learner who understands robotics, and the machine learning people say, oh, he's a roboticist who does machine learning. So I by now know neither to which community I really belong, or maybe I belong to both of you guys. Okay, so I hope it's the latter. So I'm going to present to you kind of a continuum between the two lectures we had originally planned. So we're going to start out with the policy gradient stuff and weave in a lot of robotics. And this is probably going to be helpful for the deep learning lectures, deep reinforcement learning lectures coming later today. And subsequently, tomorrow we're going to do more of the model-based our policy search methods. And in both of them, I weaved in, well, a lot of robotics. Now, I did my PhD pretty close to Hollywood, so I'll start this with a small movie. What you do see here is actually a really, really old advertisement. It's from 1969. It's from the first robot ever. That was the first industrial robot ever, and they were so proud of it, they said they'll bring it to your home. Right? I mean, they were about as proud of their AI being very successful so soon that you will have a personal robot. And in a moment, you will see that, well, how much that was overshot. So that was quite a monster as a robot. And obviously, well, they were right about one thing. They managed to turn robots into something useful within 1 decade. Within 1 decade, all of the manufacturing of cars had turned robotic, and the companies which didn't manage. Luckily, life has changed quite a bit, so the family life back then is quite anachronistic for us, but the robot in there is actually quite futuristic. And the sad part is, the way how people actually programmed that robot back then is pretty much the same of how an engineer in industry would program a robot today. And that's a really, really sad thing. So it's literally hard-coded. And yes, back then you would have to take a very fancy, highly paid engineer. Today you would take an undergraduate student. But it didn't change. Otherwise, very, very little has changed. We have more computation, we have better robots, we have better actuators. But it mostly boils down to following precisely one particular trajectory taught in through via points and interpolating. Now that was faked. That's actually the only sequence of the whole movie which was faked, the opening of the cork. And well, it gives you a feel how much robotics as a community has, well, kind of failed. Since we actually don't have these robots up to today. Luckily, well, at least in the Western world, I don't think we have the housewife drinking champagne all sadly alone anymore either. So at least in some ways we've advanced. And our robots are obviously much more beautiful still on a mechatronic side than this monster. But control principles, hacking up of the task, of the representation of the task, that has changed this little in industry. And yes, we do build cars with this greatly. Now that obviously shows you a bit of the problem. In fact, it shows you that the two most successful robots we have today, which are in the end the vacuuming robots and the industrial robots, are actually built to avoid any kind of uncertainty, any kind of adaptation. In industry, if we have had only 2 deaths so far, and they both happened because of somebody being drunk and falling into a robot's workspace, as there was absolutely no sensing, and the guy had to actually fall through a fence in both cases. Well, the robot didn't even notice, because everything is done up to sub-micrometer accuracy, and the robot is basically a physical simulation of a real system, you could say, or a real simulation of a physical system. So it really works basically like rigid body dynamics. And any of you who's bought a Roomba knows the first thing you do when you get a Roomba at home is rearrange your furniture so that it doesn't get stuck. Since literally all it does is bump against something, turn by a random angle. So you could say it's a stochastic policy, but it's a completely fixed one. And that's pretty much it. Now, in contrast to that are actually the applications which are now coming. And some are really super important. Just think about Europe getting out of nuclear industry, or at least Central Europe, where we have to now figure out how to handle a really large amount of trash completely robotically. Even worse in the UK, where they apparently mishandled their trash since the 1950s. And I don't know how this is in North America, but I can't believe they were much more careful than the European agencies either. So it's going to be really, really important. Then we're entering new regimes in robotics, regimes where classical physics no longer applies. Since in nano and micro robotics, people actually have problems where you cannot just do rigid body physics models, but you really have sometimes first order models or some really complex viscosity models which nobody really understands anymore, and where, well, the approach of industrial robots will no longer work. Any collaborative scenario in robotics obviously requires more learning, and, well, household robots, agricultural robots, and transportation all have an amazing amount of uncertainty. Now that calls for machine learning, and I will not talk about all of robot learning. In fact, yesterday you had a nice introduction to robot learning from imitation, from learning from imitation, which we also use in robotics a lot. I will not cover that today. I will really mainly focus on, well, what actually is it that we have in terms of methods in order to do reinforcement learning for robotics, and, well, how can we learn tasks by trial and error. And of course, I'm preaching totally the choir of saying that is a task for reinforcement learning, and forgive me if I'm running really quick through a couple of pretty much standard slides about reinforcement learning. I know most of you are by now, being in the summer school, total experts of this, but sometimes there are subtleties which in robotics are, well, kind of seen differently as they're seen in the RL community. So let's start basically with a classical scenario. So we want to have a policy. We obviously have also state distribution, which is resulting in this action, next state, reward loop. And in most cases, we actually want, some form of a stochastic policy in order to get implicit exploration. In some cases, though, we want to make this explicit in order to make our robot system more safe and more predictable. And what we really want to do is we want to adapt this policy of the agent to the environment to maximize the reward. And you guys obviously know one classical site. Maximizing the reward, well, obviously means that we have under some start state distribution, some policy in some system, we want to maximize, for example, the discounted reward. Discounted reward, as we have it all of our reinforcement learning, all of our classical reinforcement learning, is totally the right, for infinite horizon, totally the right problem if you have a stationary distribution and you can actually converge to it. So this is a really important aspect here. So for example, in robotics, if you want to do a task which is just about controlling a fixed point, so doing pole balancing, for example, with a robot, in this case, you really want to model this with a discounted problem and infinite horizon. Or similarly, if you have a periodic movement, where you always will come back to the same gate cycle, just as both this quadruped and this biped down here, well, in this case, you really want to model it as a discounted problem. Ball paddling, many other problems can be seen that way. In harsh contrast to that is actually a type of movement which is much, much more common in robotics than just stabilizing a task. And that's, in the end, the point-to-point movements. So in point-to-point movements, we typically have a finite horizon. A discount factor is super dangerous because it will destroy your learning performance. And we encounter it pretty much all the time. A grasping movement, a pointing movement, a table tennis forehand, a ball in the cup movement, any kind of, well, the pancake flipping, which you see back here, they're all typical stroke-based movement. So we quite frequently have to deal with a very, very different scenario to the one you've mainly been taught this week just as much. That also means, of course, that we suddenly have to live with two ways of thinking about value functions. For the stationary case, where we have an infinite horizon, well, obviously, the classical definition of the value function and for infinite horizons, both for the v and the q function, is just as we have, well, as you guys have been seeing it all week. But it really becomes quite important that when you're dealing without discount factors and you have a finite horizon, that you suddenly get a time-indexed value function, and value functions, for that reason, lose much of their power. Because you no longer have this one function you can globally use, you have actually a whole series of them, and they are by no means as useful as they were just a moment ago. So, what makes robot reinforcement learning such a challenging task, and why did this bring policy search forward so much? Well, in the end, we're dealing with a real-world problem, which has really high dimensionality. So we're usually talking about continuous states and actions. We're usually talking about a huge variety of tasks, and they have to all be learned in one framework. To just put this quickly into perspective, like let's take a robot arm, so just with a fist as end effector. Now, in a typical good robot arm in my lab, we have 3 degrees of freedom here, 1 degree of freedom here, another 3 degrees of freedom here. That basically means I have one joint angle and joint velocity per degree of freedom. So we're talking here already about a 14-dimensional continuous state space. But even worse, I have to send down accelerations or torques, depending on how I've set up my robot, at also into a 7-dimensional action space. You directly see that, well, this is beautiful, but it also means it's really, really difficult. And we can't just say, oh, well, we have an MDP from the shelf, and we take our from the shelf MDP solver, and we are done. Nope, that will unfortunately not work at all. Instead, we have to really look for methods that actually work in the real world and can live with the high cost of generating data. So also here again, we live in a somewhat different world to how people live, for example, in computer vision, where they have a big data set and, well, they can do learning directly on this big data set. Our data sets are generically small because they're limited by very few robots, and even transfer between robots is still a really, really hard problem because of tiny differences frequently in the mechanics, especially when you go to more complex, for example, high acceleration robots. And then you have, well, very noisy measurements. So in most cases, we are actually talking about a POMDP more than about an MDP, despite that I would say 99% of all of robotics doesn't admit that. They just say, oh, we use a Butterworth filter to get rid of the noise. But that introduces, of course, a lag, and, well, in the end, has made our problem actually even harder. And then we even have an exploration problem, which makes our life harder. Our exploration is no longer, hey, let's try 1,000,000 trials or trazillion trials on a simulator, but instead it's, okay, let's try this on a real robot. And we know from us humans, we humans are incredibly fast at adapting to a new system. We can learn with very, very few trials, and we know also, and that's from neuroscience, that both model-free and model-based algorithms appear to be happening, and that especially for the fast adaptation, we use a lot of model-free stuff, which is totally counterintuitive to much of the, well, RL community. So that basically means, well, we have to be super careful. We have to create exploration on a real system, not damage the robot, and it will be all along trajectories, So even our data sets are not going to be IID or, well, simple in any form. So let's look at these three challenges: dimensionality, real-world environments, and exploration. And let's see what it does to value function-based reinforcement learning. So suddenly, we would actually have to learn a value function in a, well, continuous state action space, where we know we can never fill we can never fill it up with data. And we also know that there is most likely not an easy nonlinear embedding in there, as it happens to be so frequently in discrete vals. So this filling up, of course, makes it really, really hard to scale these to high dimensions. And of course, any bad approximation propagates. I mean, that's the strength of value functions, that they propagate it very quickly. But it also means that a mistake can very, very quickly propagate. And this very, very small policy shift, like let's say a very small value function shift, can have a very, very big impact on the policy. Think of it quickly. Let's say my goal is to get to the other desk, and I can go to the left and to the right. And at the moment, both have roughly the same value, but a little bit higher to this guy. So my policy is very stable to go here. Now I do a very rapid shift because, well, some trial made me bump against the wall. So now suddenly this has a higher value. So my complete policy gets restructured, and my complete value function gets restructured along, and that makes things much less stable, and you actually can get a very unstable learning loop. For that reason, well, we estimating a global policy by really running an argmax on a Q function or a softmax acts just as much on the Q function, can be a very unstable update in such high-dimensional robotics domain. But it's even a bit worse when you think about it. If I'm searching a 7-dimensional action space in a nonlinear function, well, I have to obviously resort to gradient descent for every state action pair. So I'm actually paying a really, really high price if I'm representing actions explicitly instead of representing a parametric policy. And, well, exploration, of course, is typically in value functions uncorrelated for each time step, because otherwise our Bellman equation breaks down. And for that reason, well, what we see quite frequently is that it does break the robot quite rapidly. So happened for me, for example, my first week as group leader. I had run a beautiful algorithm, and I had some tiny bug in it, some tiny difference between the simulator where I verified things and the real system. So I was quite confident with the simulator. So everything seemed to be sub-millimeter accuracy. It turned out it wasn't, and the robot had an unstable control policy which exploited, well, some advantages of the simulator, and it made bang. Well, robot broken, right into the joint limits, robot broken, and my first week as a group leader in robotics back then meant I had to go to my boss and say, will you please give me another 10K so that I can repair my 120K robot? Well, wasn't my most favorite first week in life. So be super careful whenever you since damaging a robot is quite easy. Parametric policy methods have a huge advantage in that respect, since in the end, you have a policy. This could be, in most cases, this would be a stochastic policy, but it can also be the deterministic one. And it has a parameter vector. And what we can do with this, of course, is that we can choose it right away in an appropriate form. So we can right away choose a type of policy which we know has the right kind of features, has the right kind of advantages for our actual system. So what we really would like to have is a compact parameterization, since sometimes a policy with very, very few parameters can actually do a really, really good job. In case there's any people here who do operations research, I may actually be preaching the choir, since they learn about warehouses where the optimal value function has infinitely many parameters, but the optimal policy only has one parameter. And it's quite obvious that a much more compact parameterization exists if you do policy optimization. In robotics, of course, encoding prior knowledge is also a really big strength. in the sense that I can now use imitation learning to initialize my policy, to get a good structure, that I can use all kinds of supervised learning I have from observing an agent and directly bring it in there. Then it comes with something which is frequently considered a big disadvantage, but in practice for us is also a big advantage, since if you start close enough to a good policy, a locally optimal solution is frequently much more useful than in a globally optimal one. So when you go up by gradient ascent to the maximum reward, well, that gives you much more safer policy updates because you will only incrementally change your policy, and you don't necessarily need to maximize a value function globally over the whole state action space. What's probably the nicest, though, is that we can focus our exploration, since our exploration can quite frequently, well, exploration in the sense we've seen it with let's say a Gibbs policy, can be devastating in robotics. If you do a Gibbs policy and you run it through a robot system, it can very frequently jump between such big changes in the torque that your motors will be broken by minute 3, not by OpenAI number of trials, just to give you a feeling of how hard a problem you are at. While on the other hand, if you just basically do, for example, parametric exploration, then you can get much smoother exploration and still at a much nicer level. Having more local exploration is actually key quite frequently for human learning too. Just take the scenario, you're getting onto a new bicycle. In fact, scratch that. Even you're getting on the bicycle for the first time again after not bicycling for 2 or 3 weeks. Your body immediately does adjustments. And the variability which you have in your movements, that's not a bug of the biological system. That's a feature. It actually helps you to do system identification, and the classical adaptive control people call this persistent excitation. So even in theory, it has a really helpful use in there. Now I should say from the beginning on, there is of course a continuum between the direct policy search methods on one extreme and the value function methods on the other extreme. And during this lecture, you will hear some of the names of these methods. Some you may have already, many you will, like Q-learning, you will have already learned in all kinds of detail. And it's quite a continuum between the two, because you obviously can use more and more parametric methods, especially when you're in the middle, close to the actor-critic scenario. What's kind of important for us in robotics is also special cases, like the contextual case, where we have an additional possibility of selecting between different MDPs in which different control problems in which we're operating, or the hierarchical case where, we have both continuous spaces where we operate and discrete ones. So take the scenario of table tennis one more time. You have forehands, backhands, all kinds of strokes, and you have to actually select between them. So there's a selection layer, which is quite clearly a discrete problem, which maps continuous states to discrete actions of selecting primitives. And then there is a continuous layer where, you create torques for the robot. So let's now finally get to the outline of this lecture. And I should say, please do interrupt me at any time, since I think time-wise we're doing okay. First, I will tell you about a taxonomy of policy search methods, and really of the possibilities you have in this whole toolbox of methods which we have available. Then I'm going to focus particularly on model-free policy search methods, which where we did a lot of work in the past. And then I'm going to be talking about model-based policy search methods and, give you a bit of an overview there. So let's start with with this taxonomy. And, what we classically, of course, have is we have a data set consisting of states, actions, and rewards. and we want to use them to update our policy optimally. And in model-free methods, we obviously don't want to have any form of a model because because quite frequently getting a model that actually works is going to be harder than getting a policy that actually does the job. So for example, and in some cases, I should add this, in some cases, especially when we are violating MDP assumptions, which happens in robotics literally all the time, well, in this case, the model will be very, very wrong. So for example, if you have cable drives, these have their own dynamics, and they're actually quite vital by dynamics. You'll never be able to measure these unless you have additional force sensors, additional motor encoders, and you have a really, really good model of what's happening between temperature sensor, maybe on the cable drives. So literally things you can't even dream of having. Thus, in those cases, model-free policy search is really, really an advantage since you do not need a model. And we can apply it in pretty much many situations, but obviously we need to run, well, for every update we do, we basically, well, will have to generate new data and figure out on the real system what is going on. Again, I should highlight, using a simulator to train your robot for a difficult robotics task, that's the easiest way to break your robot. So a model-free actually works substantially safer in that context. But model-based, of course, has this huge advantage that you can use either a simulator or in many cases is even a simulator or even in some cases an analytical model. So it will only work if a good enough model can be learned. That's actually part of the conundrum here. Since if I can actually learn a model that is as good as the physics models which a really, really good engineer manages to put together, then there are actually planning methods in classical robotics which will beat you anytime. Of course, that assumes no stochasticity, no unidentified parameters, perfect knowledge of the world, continued. But under these assumptions, they can get really good trajectory generation. It's just much, much more costly than the undergraduate student whom you let do the direct robot teaching. They call it teaching when they let the student do the programming of the wire points. So optimization with inaccurate models is actually directly linked to disaster, just like my disaster with the Q function method. That was partially also a simulation disaster, and where I had a tiny enough error in there. Yes, sure.
So do you know if there are methods in which instead of separating building the model, learning the model, and then doing the optimization, you can do end-to-end, like learning to plan and build a model with an imperfect model and an imperfect planner, but that's trained end-to-end, just like policy search is trained end-to-end.
Okay, so that's actually even adaptive control, a really old question. So it starts in the early 1960s when Feldbaum introduced what he called dual control, where you do the complete Bayesian update about your system model and your state in the same kind of forward model. And kind of what we call Bayesian reinforcement learning is the discrete counterpart to that. The big problem is that for continuous systems, you literally can only make it work for one particular case. And that is, well, a deterministic linear system. Already for a stochastic linear system, the variance parameter starts to kill you. And to be good enough to get both of it together. What is a much safer thing to do is if you do separate these two steps, but you basically try to actually make your model more noisy than the reality is, so that you are somewhat robust to the problems in reality. Or you do an approximation to this full dual control, to this full Bayesian thing, and we'll get to that in the second half of the lecture tomorrow. But unfortunately, that's relatively low D and done with the GPs. So I hope that.
I believe there's more to do in that direction.
Absolutely, we all believe, but it's also very, very hard. And but there is actually some really interesting work in the classical controls literature happening roughly in the last 10 years, which is currently theoretical there, which we could probably transplant into the RL literature quite successfully. So if you look for information-based control, they actually figured out a few things which are really quite powerful. But that's, yeah, I do agree upon your point. So, okay, so today we'll mainly be talking about the model-free stuff, and we're going to start the policy gradients, natural policy gradients, then the EM-like methods, and then finally with an information geometric approach. And when you look at, well, any kind of policy search, we always have basically 3 steps. In the first step, we explore, so that means we generate trajectories and, well, following some particular policy. Subsequently, we evaluate these, and, well, in most cases, I'm writing here quite specifically, we return, because in this, for trajectories, it would be, well, the return, not just the reward or the value. And we try to maximize this and find a new policy, which should ideally be, well, still a stochastic policy in some form, or still have some form of exploration, and give us a new version. Now, in the trajectory-based scenario, well, we have typically parametric exploration. So given some context, some initial state, we want to generate, well, sequence of states hidden in the tau. Well, we want to disturb this by choosing a new set of parameters and trying them out. So in this case, our policy is actually more of a search distribution than an action distribution, or at least our explorative part of the policy. While you need a lower level deterministic policy in order to actually map states to actions, which then has these parameters, this theta. So it really has decoupled the exploration step from the mean behavior step. This can be really, really powerful. Imagine instead of you're actually steering an oil tanker. No, oil tanker, and you would do a Gibbs policy. Well, the Gibbs policy would mean you do this here all the time. Now, nearly all of you have never been in an oil tanker. But an oil tanker takes 2 kilometers before you see the first result from your action. Now let's assume you have been doing this steering all the time. You've probably done 2,000 or 3,000 steps of exploration before you've actually gotten the first bit of signal. So it's quite clearly we're washing out our signal right away if we do action-based exploration, as so frequently done in reinforcement learning. And it's dangerous for the oil tanker. It's probably dangerous too, because you're shifting around some pretty big pieces of metal. It definitely is even more dangerous to the directly controlled robot, so you really don't want to do that. Instead, what is much safer to do is if you do just, well, you perturb your policy a bit and you keep the mean behavior around for a sufficiently long time. And most likely, well, after 2 kilometers, you're going to see, oh, well, that was the Statue of Liberty. Okay, damn, that joke didn't work. I don't think any oil tankers get anywhere close to the Statue of Liberty, but never mind. So, action-based exploration, while, well, we like it, of course, because of the Bellman equation, everything which belongs to it, it also has this, well, bigger disadvantage that it washes out the signal, but it has the big advantage, of course, that it's much, much easier to quantify. So I know, for example, well, what are the torques or torque changes I can allow to my robot, and I could quantify it, and I could directly make sure that my policy doesn't exceed it. So there's also a lot of good to be said for it within robotics just as much. In this case, well, you would actually be able to also make better use of your samples, because you could use always the value, meaning the reward to come. So let's compare this one more time. Trajectory-based approaches are incredibly simple. They sometimes give us a lot of things for free which you normally don't get for free. So for example, you don't need a Markov assumption. You can actually optimize your policy if you have an unobservable system, or as Joshua just suggested, if you're doing dual control and you want to do it end-to-end, you really don't want to figure out whether you're representing an MDP properly, but you really would rather get to the most simple, non-Markovian problem, which is most likely underlying your system if you have approximations in there. And we all know we do. Then you get correlated exploration with the relatively smooth trajectories, which, well, is again very, very helpful when you're, well, steering a robot or, well, an oil tanker. On the other hand, well, really high efficiency really only happens when we are dealing, at least up to today, with a relatively small parameter spaces. So where we're talking hundreds of parameters, not billions of parameters. And well, one approach that has been very, very, very useful for us have been movement primitives, where, well, we have a very particular model class, which is, well, very good for trajectory generation based on incoming signals. You can do this largely structureless with a black box optimizer. And in contrast to that, action-based exploration, well, typically has much less variance in the quality assessment, thanks to the Bellman equation, and in theory, should be super data efficient. But at the same time, of course, you need to make sure that you really have an MDP, that you really represent the state, that you really have the right basis functions, and well, you get automatically much more jerky trajectories, and quite frequently, well, you get unreproducible trajectories just as much. And well, we need to this really has the advantage of decomposing into time steps, but also coming into the disadvantage. So this yielded a lot of methods over the years, and I guess I gotta speed up a bit. So we're going to visit a lot of them during this talk, so you will see them anyways. This taxonomy is a bit imperfect because there are obviously approaches which are hybrids of state and action exploration. So you may have heard about power or pi squared, which, well, in the end do explore in the parameter space, but do this at every time step. While there's obviously also hybrids of, well, which explore in the action space at each time step, but are applied to trajectories, like, for example, reinforce or episodic natural actor-critic. So basically, we have two ways of representing policies. One way is, which are quite common in the robotics literature, one way is that we create some form of dynamical system which we can perturb or change in order to generate generate nominal trajectories, which are then subsequently turned into actual motor commands based on the current state. And movement primitives, as introduced originally by Auke Eisbert, yet within the robot learning community, well, they have become our most important tool. The big disadvantage of these approaches is that how you bring in the modulating terms for sensory feedback is, well, I would say a bit dodgy, because you bring in a function approximator into a dynamical system, which can couple, in theory, everything, but at the same time, well, has usually some unexplored properties which are not easily accessible. For action-based representations, which directly work on actions, we obviously have the whole toolbox from supervised learning. Well, most importantly, of course, deep neural networks, which allow us to avoid much of the feature engineering and direct use of vision, but have the big disadvantage that the number of parameters and the amount of required training data quite frequently is, well, too much for real-world application. In contrast to that, well, the classical representations like linear or RBF networks have been somewhat more parsimonious and have been easier to train in the past. So now let's finally get to the model-free policy search methods, and let's really start out with the policy gradients. And well, our goal is to use a set of samples, so either gained on trajectories or gained on state action in scenarios, and either have done parametric or action-based exploration. And well, we very frequently use a Gaussian policy throughout this talk. So it's either a Gaussian on our policy parameters of the lower level policy, or it's a Gaussian on our action where the mean is dependent directly on our state. And in policy search, well, basically there have been four different ways of how we have been doing that over the last couple of years. The most classical approach for that were policy gradients, which really do correspond to to basically going with a minimal Euclidean distance to the best possible reward. Since roughly 15 years, we have natural policy gradients, which use a different version of proximity between policies, since they use the KL as a proximity, or the approximate KL using the Fisher information, and which then give you typically a better type of exploration. And then obviously there are more principled information geometric updates, which actually have exact solutions and usually use the KL not approximately but really exactly in the information-based form. And finally, there are the EM-like success matching approaches, which use the exact moment matching KL. And you can use actually all of these methods, whether you want to do it for action-based or for trajectory-based policy search. Let's start with the policy gradients. Policy gradients, our key problem is to find a gradient of either the higher level policy of the exploration policy parameters in the parametric scenario, or directly of the parameters theta in the stochastic action perturbation scenario, and update them by gradient descent, where alpha is a learning rate. The most common policy gradient methods are the likelihood ratio policy gradients. The likelihood ratio policy gradients actually rely on an incredibly simple trick, which just requires a little bit of high school math. And that trick is that, well, if you take the derivative of the logarithm of a probability distribution, then obviously this is 1 divided by this distribution times, thanks to chain rule, the derivative of the probability distribution. And you can reformulate this, of course, so that your derivative just becomes the distribution times the log derivative of that original function. Now that by itself is simple, but was largely forgotten up to 2000. And it's very, very helpful for deriving a model-free gradient estimator, because if you take the derivative of the expected return, and you have now here the expected return, and you bring this to the inside, you would now have a derivative of a function where you not necessarily have the perfect samples for. But when you do not plug in this trick, you see that we directly get get a term which relies directly on the samples, so we can actually work directly with these policy based on parameter-based exploration. Interestingly, this year is still a state-of-the-art method, even for the OpenAI benchmarks, as Ben Recht has very recently shown just again. Despite that, it's really the simplest approach in order to get parametric exploration. So, and they call it also sometimes random search. So this type of a parametric likelihood ratio gradient, can obviously generalizes directly to the action-based scenario, but it's a very high variance gradient estimator. In fact, it's such a high variance that it was considered useless for a very long time. Long before Williams introduced reinforce or any of the methods we commonly throw around, people in the simulation optimization community had already found it, and they actually considered it, well, largely useless for that reason. It turned out that a simple trick, the simple trick of subtracting a baseline, can actually substantially reduce this, is the problem there, and only using the variance of the returns, meaning the reward to come after the particular perturbation, can also does a major difference. So when you plug these in, you suddenly have this minus b. This minus b does a huge difference when you see here different gradient estimates, and you see they point into literally all directions. The expectation is the true gradient, but due to the perturbations of that, well, the respective contributions point into pretty much all of the directions, and only by subtracting out the majority of the rewards, you suddenly can direct them, and they suddenly are all within plus minus 90 degrees. A common baseline is the average reward, which works surprisingly well, but there are optimal baselines that minimize the variance and, well, do a much better job. Analogously, you can do this for action-based policy gradients, and where we would now write down, well, the distribution over the trajectories in a Markovian sense, write down the return in a Markovian sense, express the expected return through these two integrals, and once again apply this log ratio trick. Where in this case, well, we see that we have the log of the trajectory probability distribution, and this is something really, really nice, since if you take the log of this path distribution, you recognize that the only thing which has actually our policy parameters theta in there is the sum of the log policies. So we can actually completely forget about the model as long as our samples are drawn from a realistic distribution. And for that reason, well, we have a derivative of the log trajectory distribution, which really only depends on our policy. When we plug this back in, we get something which is called the reinforce estimator. And, well, it's largely credit to Williams in the reinforcement learning community. I should say there was another family of people who also came up with it independently, called Gulapalli, Benbrain, and Franklin. And they even had some really interesting robot locomotion results where they used a multi-layer CMAC. So you guys know obviously CMAC as tile coding, but they used, I think, hierarchical combination of an 8-layer CMAC in order to teach a robot to do basic locomotion. And so you could say that there was some form of a precursor to deep learning in a form with the tile coding CMAC, so somewhat. So what we obviously have, well, a lot of variance in this, in whatever that reward is. So we only want to use the returns past the current action. And interestingly, Williams did actually not use that. But it's surprisingly trivial to show that obviously a reward which comes before a particular action can actually not have an expectation which is different from 0. So this is basically just saying causality says the gradient of that policy should be 0 for any reward which precedes the action. If you plug this in, you get something which is the, well, sum of the log policy derivatives times the Q function. And that was first introduced by Baxter and Bartlett into the RL community, We today know it under the name, not so much under the name GPOMDP as Baxter and Bartlett used to call it. They used GPOMDP because they said, well, this is actually a good way also to do POMDPs because it doesn't have any MDP requirements. You could even use an unobservable problem in there. But we know it under the name policy gradient theorem, thanks to Rich Sutton's work. So, now this basically gives us, well, for both cases that we have a way to compute the policy gradients, so both for the finite horizon MDP and for the infinite horizon MDP. And, well, key thing is that we always have some state distribution of an old policy and some either Q function or return after that. Of course, we've put in some pretty big assumption by doing that. Some ones which are good for robotics, such as that the policy doesn't change a lot, such that we can actually neglect the changes in the state distribution and in the Q function. They analytically fall out, but that would require infinite number of samples. So for being practically negligible, well, that already says something about small changes. Once again, you can use a baseline. There's just one big difference. Your baseline doesn't have to be a constant. It can, in fact, now be time indexed, and it can be dependent on all the information your agent had at the time where he took the action, which led to this kind of a Q value. And once again, there is a very good way of doing this is just to use the V function, but there is again also an optimal estimator. So this initially made, well, this made people very happy in the late 1990s, but it actually turned out to be pretty complicated. That whenever you wanted to do more complex results. And we initially did not understand this until basically the work on the transfer from supervised learning from natural gradients to policy gradients happened. And the idea is really, well, is really much about a metric. Since how should you actually update that parameter? So what would be basically, if you just had a 1D scenario, be the optimal step size? Since if you do many small changes, your gradient is going to be, well, terribly slow. If you do pretty big changes, well, you're going to jump to one particular sample and get stuck there preliminary in preliminary convergence. So you really need to get this about right. And this aggressiveness in the policy update is both about robustness as well as about the long-term payoff. Now in Reinforce, William actually fixed this by having explicitly different learning rates for all the parameters which affected exploration, but that only works for, well, basically only works for the Gaussian and also just for the, well, 1D action Gaussian, where he, well, had a learning rate which directly depended on the variance, which, as it later turned out, was actually, well, a very, very useful one. And so basically, well, this aggressiveness is about exploration and exploitation, it's about robustness, and about the immediate versus long-term performance. Now, the classical gradient, of course, is about, well, the Euclidean distance, either directly in the parametric exploration policy or in the action-based policy. And the resulting step size would somehow be correlated to the size of the gradient and the amount of damage which you would allow your gradient to do. And, well, unfortunately, of course, the Euclidean distance doesn't change the type of distribution. So is there a better metric? And yes, when you look into, well, what people from supervised learning have taught us for a very long time, you need to look into information theoretic understanding. So a better metric follows directly from the relative entropy between the distribution which you may be generating and the one which you have observed, for example. And you can use the KL as a kind of the natural distance between your current policy and your next policy. And it has been used in two ways, also in reinforcement and policy search. One way is to do moment projection, where you really try to grasp both of the, here in this case, both of the maxima of that distribution you have had before with your new distribution. Or in the case of the information projection, where you have to actually focus on one of the modes, and you should recognize this has a slower convergence property because it tries to grasp both, but is obviously a safer thing to do in policy search, while using the information projection actually is a less safe thing to do, but gives you a much higher return much faster. The first time we noticed that this could be useful was actually when people tried to take policy gradients from first order methods to second order methods. And they figured out that Hessian-based policy gradients were a nightmare. First, the Hessian didn't converge until forever, simply because it has squared many parameters, and in order to get a good Hessian, that's super expensive. So it's not a cheap thing to do at all. But secondly, even when you had a perfect Hessian, it just meant that you converged faster to bad performance. So kind of the opposite of what you wanted. And then basically Shamkakade was the first to suggest, well, why don't we do instead a Taylor approximation also in reinforcement learning of some kind of KL between the next policy with the new policy parameters and the one of the current policy parameters. And that is coined by the change in policy times the Fisher information matrix. And he suggested this initially totally heuristically in this form of saying, oh, why don't we just take the policy difference in the first place? And it really captures, well, how much influence each parameter has on the distribution. If you do this for the policy, just like in supervised learning, you would do it for distribution over targets, well, you can have to solve a very straightforward problem. The problem of finding the direction which is closest to the gradient, subject to that the minimal damage to the KL will happen, where you use this kind of a, use this as an approximation to the KL. And it really doesn't matter in this case which of the KLs we take, because at second order, they're still symmetric. This gives you the natural policy gradient, and which has a really important difference to the regular policy gradient, since it's invariant to any form of a linear transformation in parameter space. In fact, even locally to a nonlinear transformation. And you can directly optimize it. You can even find an optimal learning rate eta, and it led to all kinds of understanding also for evolutionary strategy. The moment where you do it for the action space scenario, it turned out that this really complex looking distribution of the log derivative of the trajectory distribution times the log derivative of the trajectory distribution, which you initially would think is, well, should be unsolvable without a model and really complex integration steps, actually turned out to be just the sum of these log policy derivatives if averaged over them, and that all the cross terms between the other time steps will all disappear. And the result is again the same policy gradient, just in this case we have actually a much nicer Fisher information matrix. It really makes a big difference in the resulting control problems. And when you see it, the two simplest examples we can come up with in reinforcement learning, so a two-state scenario where we have, well, a state, we can either remain in it or go to the other one. It's even fully deterministic. And here you have one parameter of this Bernoulli policy, here the other one. And here you see the optimal solution. And here is a 1D linear problem with a stochastic policy and a quadratic reward. So these are the simplest textbook scenarios you can come up with. But the regular policy gradient would actually go to zero expiration here if you do not constrain it in any form. Similarly, the two-state policy gradient will result into a local optimum unless you start right here with a nearly guaranteed. So even stochastic gradient descent, no trick of second order helps you at all. The natural policy gradient, on the other hand, directly points to the optimal solution if your policy is in the right space for the problem, like the Gaussian is, or at least it is guaranteed to know about the constraints of living in a distribution and bring you to the optimal solution. So that brings us finally to this question of, okay, but how do we get this efficiently? Do we really want to compute now the Fisher information all the time, compute the gradient, and then do the update? And here comes in, well, two possibilities. One is actually that because you know the policy, you could actually compute this whole expression in closed form, and that would be relatively simple. Or you could use something which, well, we call the compatible function approximation. And well, let's first look at the closed form solution. In the closed form solution, you compute this inner expectation, and well, this is analytically possible for Gaussian policies and quite a few other ones. And this led to, well, quite a few big successes in recent years, including TRPO, and which you will, I think, hear about much more later today. So I will not go into too much detail here, since, well, in the end, this is something which obviously works in the millions of trials in order to get you, well, these really nice performances, for example, for this 2D locomotion. 1 million samples per iteration is, of course, way too much for real-world robotics. That's the reason why we have preferred using the compatible function approximation, which actually is a really interesting insight that when you have the reward to come, that there's only one unbiased function approximation which you can plug into your gradient in there. And this, interestingly, has very specific basis functions psi. These very specific basis functions are the log policy derivatives. This directly relates, by the way, to soft actor critic and a lot of other things which represent the KL constraint differently, because for them this, for the easy case, you could analytically derive this as well. So the log policy derivative actually tells you the optimal features for your value function approximation if you use it as a statistic in your policy, in your natural policy gradient descent. The big problem, just of course, is that the baseline in there, which still remains in here, well, makes the problem quite hard in terms of a function approximation problem, because you're no longer approximating a value function then, but you're actually approximating an advantage function, which is the difference between the Q and the V function. And when you plot, for example, the Q function of LQR, it's a quadratic, but the advantage function is actually a saddle. It's neither convex, it has no good properties, you can actually not do any form of TD learning, and it's very, very easy to, well, implement something wrong, because you have to use something in addition in order to make it work in the first place. Of course, you can sometimes use it directly on Monte Carlo rollouts, but that's kind of like approximating a squared function by a line. So, now when we plug this in, though, we see something really amazing, because when we plug this compatible function approximation in, we see that we once again have just the Fisher information here times the parameters of this compatible function approximation. Once you put this together with the natural policy gradient, you see that, well, the Fisher information and this weighting of thanks to the compatible function approximation, cancels out, and you just have to figure out the W's. This can be done, well, if you have additional basis functions by the V function, where bootstrapping can really reduce your variance, or you, well, but it also of course requires that you have to figure out value functions in the first place. And you have to, well, you have to be very careful about the bias. Alternatively, you can actually unroll this value function, write down the Bellman equation, write it down in terms of the compatible function approximation in some V, and then subsequently do this for every time step and sum it up. And when you sum it up, you get one equation per trajectory. And this one equation, well, allows you to estimate this parameter. So of course, this is super, in one way, inefficient, because you have to do average over multiple trajectories in order to get this right. And you have to assume that you have a start state distribution, which is also a pretty big assumption. But if you plug this in, you actually get a linear regression problem, where now the phi's in here belong always to the log policy derivative sums, and the one corresponds to the expected return. And you now just solve this linear regression problem in order to get you the natural gradient. And this actually shows you an example. So we take the robot by the hand, do an imitation learning scenario first in order to give it a first start. And subsequently, you see roughly every 15th trial, the robot gets a reward on the distance the ball travels, and it gets a punishment for the joint speed it does on average. And it actually can, if you have very well tuned, have the algorithm the learning rate very well tuned, you can reach a performance which gets a good hit after 150 to 300 trials. For a badly tuned version, you can nearly always make it at least under 800 trials, which at the time of that experiment was actually pretty, was the best acceptable performance we had seen so far. Today we would obviously be much faster. But you need to put it in perspective. Now that was still during my PhD, so you need to put it in perspective. This requires taking a ball, putting it onto that T-stick, going back to the robot, doing a next trial run. So we are talking about 5 minutes PhD student time per trial. We would never be able to do 1 million trials per update as so common today. So far, what have we seen? Well, we have seen that policy gradients have been dominating things quite a lot for a while, and they in the end have led to first really nice robotics results. But these approximate information constraints, they can be very easily implemented through the Fisher information, but and they do make the exploration then easier, but we can actually do this still better. And that doing things better comes through the exact information theoretic update. And there we actually realize that this kind of a problem of maximizing the return subject to a constraint can in most cases be solved analytically. And I'll give you in the last 7 minutes of today's lecture a quick example. Here you have very few trials which you have run. You see obviously the true return function, and the maximum at the moment of these samples would actually be here. And when you run this more, you obviously recognize your explorative policies was pretty bad. So you want to actually focus more. So you check out a few more trials. Only you become more and more certain over time. But you can actually, if you have too large an initial exploration, you will always get to a good solution, but you will try a lot of bad things even if you're close to a good solution. On the other hand, if you do small exploration and you start somewhere where it's bad, you may never make it to the optimal solution and really get stuck at your local maximum. So for that reason, much of the current state of the art has moved to not just using the KL constraint on the damage to the policy, but to also make sure that the loss in exploration of the policy is bounded, and that there is another big constraint in there, which again is still doable analytically and gives you, well, allows you to do parametric exploration. And the entropy here really serves as a measure for uncertainty. If you do this, you actually have, well, if you have no entropy loss bound, you would get for too small a starting thing exploration, or too small update, you would get bad performance, preliminary convergence, while if you do this with this additional entropy loss bound, you can actually get to the optimal solution in a relatively nice time. Here are the actual update equations for the policy. So you get an exponential reweighting, which is, well, made smaller by both the exploration Lagrange multiplier and by the one coming from the loss information and by the one from exploration. And well, if you obviously need to enforce Gaussianity always in there. And this has led to the Moore algorithm, which is actually still is now one of the standards in that area. Oops. You can make this even more efficient, of course, if you make sure to stay in the right parametric form of the Gaussian and always bring it back into that, so that at least you have locally a Gaussian, that you're locally quadratic, and obtain these by regression. So you, in this case, have a surrogate onto which you're always going back as an approximate step, and will interpolate in the natural parameter space. This actually worked surprisingly well in, well, in this case, only simulated table tennis, and this is it still has to move to the real thing. But what you basically see here is how well Moore would work if you have both of these constraints in there. Actually, reps doesn't do so badly, so we're talking here about hundreds of episodes, so this times a factor of 12. So within hundreds of episodes, we get to a good performance already, while, for example, going with a CMES, with natural evolution strategy or CMES, you're much worse. Okay, for the sake of time, I think I will skip these things and simply summarize what we've been doing so far. So you could again use use this now as a compatible function approximation in there. So we recognize where this whole thinking came from, and do this also for the Q function, and obtain both baseline and Q function by LSTD. And well, this gives you, well, one version of the complete algorithm. Now for the state action version, where with a stochastic policy linear in the states. And this becomes, well, quite a bit better than our previous approaches, is based on just Moore and reps. So let's hope these videos work. And then I think we can wrap up already. So you see kind of the difference in performance. So, alrighty, so in the end, these information geometric constraints have really helped us at well, efficient computation of the full covariance metrics, and you can do them both in the trajectory-based as well as in the action-based scenario. And well, the entropy regularization really is helpful for avoiding premature convergence. There's a tight connection between, well, all of the natural gradient stuff, Moore, reps, soft actor critic, and TRPO, since in all of these cases we're trying to use the natural reparametrization, which is log linear, and they all are at least locally equivalent, and except for obviously the vanilla policy gradient. But only the natural gradient is actually fully exact if you don't do anything further. So I think now I have 19 seconds left, and I've taken way too few questions, and I've probably been way too zombie thanks to my headache / jet lag zombiness today. I promise you tomorrow I will be less zombie. In the worst case, I'll take the aspirin earlier. And I promise you that you see the most fun videos on robots tomorrow because, well, they actually start right at success matching, most of them. And yeah, I guess I'm out of time even for maybe 1 or 2 questions still.
Yeah, we have time for a couple questions.
That would be great.
So I have a question about the natural gradient. So I think that there's been some concerns about how it's computed or like the extra effects or artifacts that are introduced to the natural gradient, which is I think why K-factor was introduced.
Can you talk a little bit louder, or can we have the microphone maybe?
You have to speak up.
Yeah.
I'm really tied to this microphone.
Okay.
Yeah, I'm just saying that. Do you have any any intuition as to maybe like why K-fac, or you've heard of like how K-fac like works and everything? So I'm just curious about your like intuitions about it, instead of using a natural gradient. Or do you think that we should stick with a natural gradient?
Oh, I don't see the relation right now.
Yeah. Might be an offline question.
Yeah, I think this is an offline question. Actually, it's an interesting question. I mean, I don't think the natural gradient is the solution. It just points us into the right direction. And pun unintended.
One more question. You studied the A, you talked about exact definition geometric function. I just wonder, are you talking about the kinematic model, about the roller arm, or what?
Okay, no, I'm just talking about the update that based which is exact here. So not anything about the system or model in this case.